Welcome back. Hopefully you have a little intuition now of what the curl is. Now let's actually compute it, because if your sole goal is to pass a test and not understand the nature of the universe, which I think would be sad, but if that is your goal, you at least need to know how to calculate these things. But it's even more fun when you know how to, when you have the intuition, and then you'll hopefully never forget it. But we'll take the curl of a fairly fancy vector field, one that I have trouble visualizing, but that we can mathematically chug through. So let's say our vector field, and I'll do a three-dimensional vector field just to do a fairly complicated example. I'm just going to make it up on the fly. So let's say in the x direction, the magnitude of the field is, I don't know, let's say it's x squared y sine z in the x direction, plus, I don't know, let's make it x y squared z in the j direction, or the y direction. And in the z direction, I don't know, let's make it cosine of x times cosine of y in the z direction. Now, we said that you can view the curl of this vector field, and I have no intuition of what this vector field looks like. I just made this up. Maybe we'll graph it for fun, just to see how messed up it looks. But we said this curl, you could view it as a cross product of our del operator and the vector field. Well, when you were using this engineering notation, when you have a vector broken down into its x, y, and z components, or its I, j, and k components, you can take the determinant of that matrix when I showed you how to compute the cross product to figure out the cross product. So how do we do this? So the cross product is going to be equal to, I didn't have to draw a straight line. So how do you take the cross product of this vector field and the gradient operator? Well, you write I, j, k on top, like you're taking the cross product of any two three-dimensional vectors, and then you take the first vector, but in this it's really a vector operator, but it's this del operator. And what are the components of the del operator? It's the partial derivative with respect to x, the partial derivative with respect to y, partial derivative with respect to z. Right? Let me just rewrite the del operator. You could view it as being equal to the partial with respect to x I plus the partial with respect to y j plus the partial with respect to z k. Right? So it's x, y, and z components, so the partial with respect to x, with respect to y, with respect to z. And then the second, where we're taking this operator cross the vector field. So what are the components in the vector field? I'll probably run out of space, but it's x squared y sine z, and here it's x y squared z. I should have written all of this bigger. And then in the third column, the z component is cosine of x times cosine of y, right? Just the x, y, and z components. And now we are ready to take the determinant, which will probably, well, it'll probably get pretty messy, but let's try it. So this is equal to the I unit vector, let me use a more vibrant color, the I unit vector times its subdeterminant. So you cross out its row and column, and so you're taking the determinant of this expression, so it's going to be times, well, this times this, but it's really the partial. If you multiply the partial with respect to y operator times an expression, you're really just taking, since it's an operator and not an expression, you're really just going to take the partial of this with respect to y. But I'll write it down. So it's going to be the partial with respect to y of cosine x cosine y minus the partial with respect to z times x y squared z. And now we're on to our j component, plus j. So now what's the magnitude of our curl in the j direction? Let's cross out the row and the column of j. So it's the partial with respect to x of this. So this is maybe messier than I originally intended. Cosine of x cosine of y, across these columns there, minus the partial with respect to z, minus the partial with respect to z of x squared y sine of z. And then finally our k component. Oh, and sorry, when you take the determinant, you use the kind of and this is all kind of a bit of voodoo, but you put a plus here, a minus here, plus here, so it's kind of this checkered pattern. So this is plus I, this should actually be minus j. Don't want to make that mistake. This is minus j. This is just kind of the algorithm of how do you take a determinant. Okay, and then finally we have plus k times the determinant of its submatrix. So the partial with respect to x of this, partial with respect to x of cosine x. Is that right? Oh no, sorry. We take out its row and column, so of xy squared z minus the partial with respect to y of this. Where we took its row and column, so this is the submatrix of x squared y sine of z. Alright, now let me try to simplify it, and I'll have to get some space. Hopefully you understood what I did here, and now we got this. And now I think I can erase all of this, and just so I can have some room to simplify things in. Just as, no, that's not what I wanted to do. I wanted to do it in a darker color. That's what I wanted to do. Erase that. Erase that. Now we just have to simplify it. Taking a bunch of partial derivatives. What's the partial derivative of this with respect to y? Well, x is just a constant, so it's going to be, well, we could just put the I out front, but eventually we want to write our magnitude before the vector. So it's I times the partial of this with respect to y was our constant. Cosine of x is just a constant. And then what's the derivative of this with respect to y? It's minus sine of y. Right, so we'll write sine of y. And let's put the minus out front. Right, these are what's multiplied. Okay, and then we have minus. Now we have to take the partial with respect. Sorry, actually, I forgot to do this part. Let me start over, actually. So, let me just take this expression, then I'll multiply it by I. The partial of this with respect to y is cosine of x times minus sine of y. Let's put the minus out front. Minus sine of y. Sine of y. Now minus the partial of this with respect to z. Well, if this with the partial of this with respect to z is xy squared is just a constant, right? So the partial of this with respect to z is just xy squared. So minus xy squared. And then we're going to have all of that. That's the magnitude in our I direction. And now we have minus, right? Because minus in the j direction. What's the partial derivative of this with respect to x? Well, the partial of cosine x with respect to x is minus sine of x. So it's minus sine of x. And cosine of y is just a constant, so it's just carries over. Cosine of y. And then that should be, oh yeah, there we go. Minus this expression, the partial of this with respect to z. Well, the derivative of sine of z with respect to z is cosine of z. This is just a constant, so it's minus x squared y cosine of z. And that's the magnitude in the j direction. We're almost there. And now, finally, plus. What's the partial of this with respect to x? Well, these are just constants. So it's y squared z minus. Once again, we just have a y term. Everything else is a constant. So the partial with respect to y is x squared sine of z. And that's the magnitude in our k direction. And we're pretty much done. I mean, we can simplify it a little bit just to make it clean. I mean, essentially we could just, I don't have to rewrite it. We can just multiply this by -1, so this becomes plus, plus, plus. And yeah, that's pretty much it. This is the curl of the vector field V at any point x, y, and z. So that's how you calculate it. You just literally take the cross product of that del operator and your vector field, and you'll get something fairly hairy, although this was, I think, a hairier than average problem. In the next video, we'll do a little bit of this, but I think it'll give you more intuition and less of just the algorithm and the computation of how do you do it. See you in the next video.